Good morning to everyone. A warm welcome to all on behalf of InfoChip and Asia Gujarat section. Thanks for joining a online webinar on robotics, fundamental, application, and futures. Today, here with us, Dr. Nagendra Gajjar sir and his team, Dr. Jatin Kumar Dave and Professor Vishal Vaidya. Dr. Nagendra Kumar Gajjar, Professor of Electronics and Communication Branch, Nirma University, 33 plus years of experience in the field of teaching, research, and industry. IIT Delhi alumni, research project for ISRO and DRDO, IST National Award, CVM4, and Best Engineering College Teachers in Gujarat. I welcome on behalf of InfoChip and IESA, Dr. Nagendra Gajjar sir.
Thank you for inviting us to deliver a webinar. Thank you for inviting us to deliver a webinar series on robotics, fundamentals, application, and future. This is day 2 for this particular webinar series, part 2. Yeah. So let's do a recap of what we have done yesterday. So we are a team of people from Institute of Technology, Nirma University. So the day 1 proceeding, a quick recap. Yesterday we have talked about the introduction and overview of robotics, global scenario, working groups, research, etc. Types of the robotics, the key components of the robotic systems in a mechanical structure, key components of the robotic systems, electrical, electronics, and sensors, as well as considered about the design consideration and challenges. So for the day 2, the part 2 of this particular series, today we'll be talking about the standards around robotics, industry adopted interfaces, implementations, and the mechanisms and the laws. The second session will be on different types of robots. The third and the important session for the day will be the case studies and applications, which will be taken by Dr. Jatin Dave, the practical implementations, the kind of software and the hardware platforms and the mechanical structures that can be designed using simulations and later on to be converted into a practical hardware. The next 2 sessions will be on robot operating systems, which is going to be the futuristic way of looking at the robot implementation. And then the future of the robotics, just to give you a glimpse of where the industry, nation, international level, global scenario is going, as well as giving you some kind of an input where your curiosity, innovations can help the world to build the next generation robotics, as well as the applications. So the approach for this particular webinar yesterday we talked about is what, how, and why. So the first session we talked about what is robotics, the fundamentals of the robotics. How we talked about is the mechanical and the electrical components, and some of the part of the how we'll be talking about the standards, and as well as explaining through the case studies and applications. The why part is the application and the future of the robotics. So that's what is the approach. So we have seen the part 1, half part of how and what. Today we'll be talking about the another half part of how and why. So the definitions we have given for the robots was that it's a automatically operated machine that replaces human effort, though it may not resemble the human beings in appearance or perform functions in a human-like manner. So the robotics is a branch of engineering discipline which talks about the design, construction, and operation of robots. So that's what we talked about the definitions yesterday. Definition of the Merriam-Webster also was reflected. So those who are joining today, you can refer the presentations of yesterday. Very important thing as far as the robot design, construction, and application is concerned. Once again, I'm repeating because the standards for the robotics is based on these laws only. So let's once again have a relook at it. A robot may not injure a human being or through the inaction allow a human being to come to harm. So this is the law one which is to be followed if you want to design any robot. The second law is a robot must obey the order given it by human being except where such orders would conflict with the first law. So the law 2 says that the robot must be under the control of the human, and that has to be, and it has to see that it doesn't violate or conflict with the first law. And the third law is talking about that the robot must protect its own existence as long as such protection does not conflict with the first and the second law. So these are the three laws that has been defined definitely over a period of time. We all know that the laws needs to be changed. So over a period, these also. So that is from the futuristic point of view, these laws are to be modified or say some amendment or addition has to be there as a part of it. So now let's look at the today's session, the first session, the standards for the robotics. The first thing is the why we should go for standards for any damn thing that we are playing with. So number one is that whenever we are defining standards, we look at a common measures and definitions in robotics and automation. So if you remove the last two words, robotics and automation, it is a common definition for the standards that we must have a common measures and definitions. A simple example to explain to the layman is that if you are in India, we have some standards for the plug and the socket for the electricity. If you are in US, you have a different standard for the plug and socket. Now, if you get a charger for Apple, that charger cannot work in the Indian socket, right? So there are standards available. Similarly, if you look at the Europe, the plug and socket standard are different. So standards are basically we mean by is a common measures and definitions. Similarly, in a layman language, if you want to purchase shoes and you want to get it from Europe or maybe USA, the size standards are different, right? Here we may be using an Indian or Asian standard of number 567. Maybe in Europe it is being referred as the number 41, 42, 43, or maybe in US that standard sizes are different. So that's what is the standards are very important when we mean by is a common measures and definitions. The second thing that is important for the standard is that measurability and comparability of robotics and automation technology. How do we have a measurement system, the metrology and the comparison of my technology, right? A simple example at the later on we will talk about is that we want to do some kind of installation across the global mechanism, right? Suppose we have designed an industrial robot and then measurement is to be done in inches or in feet, or say it is to be done in centimeter or say into the meter. So what are the ways I am doing a measurement system? Similarly, you want to have a standards are there. So you want to compare. Now we used to call it as if you want to compare an apple, you have to compare it with an apple only. You cannot compare an apple with banana. So if you want to have some kind of a comparison, there also you need to have some kind of measurement systems and comparison criterias or parameters. So that's where also the standards comes into the picture. It's not only the robotics and automation. Once again, I'm reiterating, it is a kind of a standards. Why do we do the standardization for any system? And the third thing that you should look into is integrity, portability, and reusability of robotics and the automation technology. So suppose I have designed a system or a unit which I'm using it for an industrial robot. Can I use the same system and reuse it into entertainment industry robot? Can I use the same for the kind of a medical representation? Suppose if I take a computing platform and which has a capability of artificial intelligence and machine learning, I need not to reinvent the wheel. I need not to redesign the computing platform. The same platform, I can use it for my purpose of a different segment or a domain of the robotics. Similarly, when we talk about is a portability. So portability is also one of the mechanism of the standards that we look at, that can I use the same thing across the global scenario. Integrity is a kind of mechanism that we look into, is that we have a common interfaces standard so that one unit can fit it into the another unit. A simple kind of a mechanism from the layman or a kid's point of view is a Lego, or we have a kind of a game for the kids where we fit in the modules and the module gets fit in. So that's what is integrity, portability, and the reusability that will help you if you have follow some kind of a standards. So that's what is the standards are very important aspects, as well as in general anything that you want to use it across the industry, use it across the society, and so and so forth. One important aspect which I have not mentioned over here, which will be coming into the next slide, will be the safety standards, which are very important aspect as far as the robots are concerned. In general, safety standards are very important because whenever you have a mission critical applications or a safety critical applications, in such kind of applications, your safety standard matters a lot, and it has to be properly followed. Otherwise, you may have a loss of human life, which is not accepted at all in any domain of applications. So some of the common standards, if we talk about, I cannot touch upon all the standards within 15 minutes of the time that we have allocated. So some of the standards are being given at an international standard organization. We call it as IESO. And for robotics, it is a technical committee 299. Okay, so that's what is the kind of a standards that are defined for the purpose of robotics. Those who are interested, I'll be clicking the website and show you. Then we have industrial robots safety standard is there. Then we have a personal care robot standard. We have a collaborative robot standard. We call it as cobots. So if you see it, the standards numbers are there: 2011, 2014, 2016. They are the kind of years in which these standards are being published. And then we have a security standard, which is IEC 62443. So when you are designing a robot for industry, or you are designing the robot and deploying it into the field, you need to provide the certification, or say you need to give a guarantee that these standards are being implemented. Just I'll click on it just to show you. So these are the kind of standards that you can see here, right? Robotics based methods for exoskeleton type walking Raka robot. Okay. Then we have a standard for collaborative applications. We have a robotics vocabulary standard, right? With the help of the new generation IT technology, you can design the robot and the robot can speak in any damn language, right? But what kind of vocabulary that you are feeding it into? And if you want to do the translation, how does it happen? Then manipulating the industrial robots, performance criteria and the related test methods. Then we have a mechanical interfaces, right? We have industrial robot mechanical interfaces such as shaft. So for all this stuff, yesterday we talked about the PPP model, RPP model, the rotational representation, and so on and so forth, the degree of freedoms, and so there are standard interfacing standards. Similarly, robots and robotic devices, the motion nomenclatures, then manipulating the industrial robots, robots and robotic devices, safety requirements. So these are the kind of long list of standards available, and that standards needs to be followed when you are actually implementing it into the professional field. So if we go further, one another thing that if you look at is ISO, suppose say 10218, how the standards are being referred. So it contains the requirement for industrial robot, and the standard is being referred as -2, means it's a version 2, which contains the industrial robot system requirement along with the controlling hazards. So the specification, so here you can say that it focuses on hazard identification and risk assessment, design requirement and protective measures, and verification and validation of the safety requirements and the protective measures. So this is how the standards are defining, and then what are the focuses of that standards that needs to be. Similarly, one another standard on the extreme right, you see it focuses on collaborative industrial robot system design, requirements of the collaborative robot system applications, verification and validation. So here, now yesterday we had a last session of design consideration and challenges. So when you are designing the robotic system for the industry or maybe for a specific application domain, you definitely need to consider the standards at the start itself. Otherwise, what will happen is that you have designed and everything is done, and then you try to put it, suppose not military robot that you have designed, and you want to sell it to the defense organization or a defense systems or government, then they will be expecting the standards are followed or not. Otherwise, it will be rejected. So at the time of your design system consideration, you need to consider all these standards. So standards are very important when you are choosing your design system. So some of the standards numbers I have mentioned over here. So one thing is called as a functional safety of electrical and electronic and programmable electric safety standards. It's a very popular standard. We call it as a FUSA, F-U-S-A, right? So actually it is a 60262 standard, but different standards are there for a different application. Today there are two major field where people do a lot of work. One is the drone industry, designing the drones. The second is ADAS, that is an automatic driver assisted system for your next generation cars. The ADAS, you have a level 0, 1, 2, 3, 4, 5, and that levels, they will be having a different FUSA standards. We call it as a functional safety standards, right? So here you can say manipulating industrial robots, manipulating industrial robot mechanical interface. So this is what I mentioned about it. So these are the different standards. We have a standard for the mobile robots also. So yesterday you have seen some of the mobile robots mechanism also, right? Now, what are the industry-based practices that we should look for when we talk about the standards and the best practices? So we have an NIST framework for improving the critical infrastructure cybersecurity. So when we talk about the robots, it has been deployed. The today's generation, we all know that the cybersecurity is becoming very, very important aspect. Similarly, the secure coding practices so that your software is not being tempered. So that is the SEI cert is one of the mechanism. NASA's power of 10, that is the rules for developing a safety critical role. Microsoft security development life cycle is there. Then we have most dangerous weaknesses. So for the coding purpose, those who are into the coding, there is a standard called as a C program. C++ programming is a common for the hardware system, embedded system programming. We use a MISRA C, right? So MISRA C is a motor industry algorithm, say coding mechanism, software coding mechanism which has been developed. It's called as a MISRA. So that is the kind of safety mechanism and the base coding practices are being used. IEEE, that is the Institution of Electronics and Electrical Engineers, also has given some software security design flows mechanism, as well as NIST is at US government has developed a platform which talks about some of the software vulnerabilities which can be reduced. So these are some of the references which I had referred for showing you standards. Those who are interested in looking more into the detail about the standards for the robotics, you can go to ISO.org, IEEE, that is Robotics Society is there. Then International Federation for Robotics, IFR. Then we have Occupational and Health Administration. That also is defining the standards. Then we have global robotic standards, as well as you can refer a website of Robotics Tomorrow, which talks about some of the application domains as well as the kind of a standards which is to be used for the purpose of robotics. So these are the references. Those who are interested in going more into the detail, you can. And if you have any questions on this very quick review or overview of standards for the robotics, feel free to ask. Yeah. Yes, any questions? Okay, if no questions, I can take it at a later stage. Let me check. Yeah. So if no questions, we can take it at a later stage also. Now I invite my colleague, Professor Vishal Vaidya, who will be talking of different type of robots, and he will be explaining about it. Yeah. Over to Professor Vishal Vaidya.
ना खाली लाइव चेंज कीजिए.
Okay. Thank you, Dr. Nagendra Gajjar, sir, for sharing valuable information about the various standards and all. Now I welcome Professor Vishal Vaidya, sir. He is working as an assistant professor in the Department of Electronics and Instrumentation Engineering, School of Technology, Institute of Technology. He has more than 13 years of experience in the field of teaching and research. He obtained his BE in Instrumentation and Control Engineering and ME in Applied Instrumentation for the Gujarat University in the year 2004 and 2014, respectively. He has published research paper in area of robotics, control, and embedded application in international journal and international conferences. He has successfully completed one minor research project funded by Nirma University in area of robotics. He has guided many UG dissertation based on robotics and artificial intelligence. He has guided 8 Idea Lab projects, from which one project was awarded as a Best Idea Lab project. He has provided mentorship for students having a project under India Innovation Challenge Design Contest organized by Texas Instrument in the year 2015 and 2018. He has served as the member of Board of Study. He is currently pursuing PhD at Gujarat Technological University. His area of interest are robotics and control, AI algorithm for learning robotics. I welcome Professor Vishal Vaidya on behalf of eInfoChip and IESA.
Okay, good morning, everyone. Thank you for my introduction. And as I said, that this is a robotics related topic, and that we need to go for the robotic related all the different types and then related projects so that you can enhance your knowledge in the field of the mobile robotics. So I start with the types of robotics that in which that mobile robot has a very variety of types, which is very useful in navigation researches and other applications of the industries, which you can go through over here. Okay, so as you can see that this is a webinar related to the mobile robotics, and then I'm just giving you the brief idea in short about the types of mobile robots which is useful in the field of the education system as well as in the industry. So that is the agenda of the session is like you need to know about the mobile robot platform whenever you are using it in any applications or any industrial agendas. So different types of mobile robot I will brief that exist in the world. It's not limited to this, but we will obviously explore the some of them. Concept of omni-wheel drive, which is mostly used and widely used nowadays in any industry applications. And there is a motion trajectory because as I said, these mobile robots are specifically designed for the navigation purpose and its challenges because there are in the mobile robots only the challenge is the navigation. So because he has to move with its own controller algorithm automatically. That is the reason that are the many challenges in the navigation purpose, and that's why people are using different types of robot which can be implemented for their relevant applications. So if you have specific application in the field of industry or in the field of education system, whenever you need to first choose that the which type of mobile robot platform I need to work with, and that is why I'm just giving you the little bit demo of the trajectory motion trajectory of the some of the video which was taken at our college premises, and why the types of the mobility is required in industrial applications. Move on to that and about mobile robot platform. Nowadays, you may heard about that. There are the so many things has to be lifted in a transportation in the industry from one place to another place. That means there are the some tools at the storage area and it has to be picked up from that place to the service station place in the car manufacturing applications or any process industry you name on. So there are the mobile robot platform. They are divided actually right now in two categories. Let's say automated guided vehicle as well as autonomous mobile robot. The future is about the autonomous mobile robot. Why that is the upcoming challenges because I'm going to tell you that about at the end. But as you can see in the image, these are the actually the applications of the industry where the mobile robot platform itself, the loading the entire car body to maneuver inside the industrial plant, and robotic arm has to work on it, or if it is fully automated. So the navigation challenge over here is that the robot has to stop at the specific place and specific position, otherwise the work cannot be finished with the accuracy, and that is the biggest challenge with the field of the mobile robotics. And you need to choose the perfect platform that can take the load as well as it can maneuver within the given environment of industry. So all the entire car or any particular tools or any objects in the industry are lifted by the these particular mobile robots. And you have seen that there are the transportations and some of the you can say that courier transportation industries also has used the mobile robot platform which navigate all the couriers and everything from one place to another place. So that are the applications regarding the mobile robot platforms. So first thing first, you need to understand what kind of different kind of mobile robot drivetrain exist in the world and why people are using them for what their purpose. So that if they are different by their designs, that means you need to take control of them with the maneuverability as well as the motion controls. So I'm going to give you the brief idea about that five types. Obviously, right now it is visible four. The fifth one is in the next slide. And the four types of differential drive robots are there, and tricycle drive robots is there, synchro drive robot is there, and Ackermann steering drive robot is there. So they are the drivetrain names. Okay, so whenever you are going to use or purchase or any mobile robot platform, you need to define what is your application, and based on that application, what is your surface area that you want to move the mobile robot. If it is industry, if it is a rough area, if it is in the garden, or any particular floor based applications. So that case, the three different or four five different kind of mobile robot platform exist in the world. Now first we take about the generalized idea. I'm going to give you the differential drive. What is this platform has been differentiated among each other, and then how they provide the motion. Motion means what? I'm trying to say that you just need to move forward, backward, left and right, and in any direction, particularly if you want to move maneuver, just like any mobile robot platform moves in your industrial office area. Okay, so differential drive means what? They have the two different motors. You can see that two different motors are there, and the speed has been to be differential, or sometimes the direction of the motor speed has been reversed. If this means what? Suppose, sorry, suppose the right wheel has been said as a forward direction and left wheel in a reverse direction. So definitely this particular mobile robot platform will move on to the left hand side, and vice versa for the right hand side. Forward, obviously, that's the motor speed and direction will remain in the same direction. Speed has to be controlled at the differential. So that's why the differential drive is there. Obviously, there is nothing relation with the differential word with the car differential drive system, but it is the difference of the speed has been created, and that is why this thing has been incorporated. Second one is very easier one, tricycle drive design, and which you can see that it's a three wheel actually, and you can only design like this way where the front wheel has been rotatable from left to right. So it's like a auto rickshaw. You can consider that way. It's easier way to maneuver in the industry because of this front wheel has the capability to moving left and right with certain angles. So while taking the sharp turnings and something like that way in the industry, you can see that there are the motor connected along with the vertical axis of the particular mobile robot drivetrain such that it can rotate towards the left and right easily. And whenever you want to maintain the direction control, you can easily do that. So it will be easier compared to others. That is the main advantage. But it's restricted to only three-wheel design. That is the reason most of the people are less using this kind of a design. However, in the industry, automatic guided vehicle mostly are using this tricycle drive design, in which the front will be rotatable to left and right using another motor. So they are driven by the back wheels. Obviously, two wheels are having the different motor. They are driven by that way. But front wheel has a vertical motor which can rotate the vertical assembly, front wheel assembly, sorry, in the left hand direction and right hand direction. Some of the sensors are shown in the diagram. So that is based on application. When you go to bypass some obstacles at that time, you require some kind of sensors. Otherwise, the normal driving mechanism is feasible to use using the tricycle drive. Synchro drive, it is rarely used, and most of the NASA people working with this kind of a robot because they want to maneuver entire the mobile robot platform in any direction without rotating the entire body platform. So this is a topple down view of the entire robot assembly. It is similar to like this way, but you can design your own also. There is no restriction in that. It is a chain driven or individually vertical axis driven, in which the and all the four wheel assemblies are rotated in simultaneously in same direction. So if you want to move on towards the 45-degree left hand side, let's say, so all the four wheels has to move the 45-degree left hand side. So then that will be easier to give the forward command, and then the entire robot will move the diagonally 45-degree. So that will be easier. And even though best advantage over here is that without rotating, you just move to the sideways also. That means you just rotate the all four wheel assembly in the synchro drive to the 90-degree angle right hand side or left hand side, and then you just give the forward or backward command only, and then they will rotate from their own position. They can rotate towards the right hand side direction or left hand side direction with the totally 90-degree angle. So the angle consideration while moving in a restricted area where the flow plan is with the so many dynamic and static obstacles are there, at that time this kind of synchro drive system is very easily available and useful also. But main point is that you need to provide the all different motors for individually wheel assembly. That means they need all the individually motors also given to the wheels, as well as another four set of motor is being given to the vertical axis of this wheel assembly. in which they have to rotate either some direction, left and right, to some angle. So that is the possibility. Otherwise, it's difficult in a design constraint also. So that you need to take care while designing the synchro drive, that the orientation of each wheel must be exactly at the same angles. Otherwise, they maneuver in random fashion. So motion control is little bit easier, but as well as you need to take care some of the parts while doing some motions with the programming. Third one, sorry, the fourth one is Ackermann steering drive. It's as per the name suggested, it's a standard drive steering kind of a drive. It's, you can say that this assembly is a car-like design, and Ackermann steering drive is has made the assembly of the front wheel just maneuver like a steering, and you can just rotate towards the right and left extends with some angle restriction. Obviously, they cannot rotate totally 90-degree left and right, but at least up to 50-degree to 60-degree possible, just like that. And one thing you need to make sure while designing this thing, because it's a mechanical design, is hardly constrained over here, where the angle of the two will be different. It's not going to be same. Otherwise, it cannot rotate the entire floor area. I cannot be rotatable and circular motion, in a circular motion. So that's why if you put the same angles, then it cannot rotate the entire body in a circular motion. So otherwise, if you take care that part in a design itself, then it will be very difficult, very easier to understand the motion control of the Ackermann system drive. Now, the fifth and most important drive right now is the Omni wheel. As suggests the name, you can rotate and maneuver in any direction at any time. This is the best platform people are right now using, even in the industry, even in the robot research projects. So left hand side, you are saying that the yellow color body platform is there, but here the difference is that the wheel design is not normal wheels. In earlier 4 cases, you can use the normal wheels. Okay, but here the wheels are different in design. Whatever you are seeing, that it's just a plastic design with the rollers, rubber rollers are attached on that. Here it is on the 90-degree on the left hand side, yellow color robot, and on the blue color robot, it is at the these rollers, rubber rollers are attached on the diagonally. What is the advantage in that case? So once you rotate any of the wheel in that direction, it will be moved. So direction control will be as easier over here. But only thing is that you need to take care about the front side of the robot where it is heading towards. And that is the first challenge that comes in this section. Otherwise, it is very easier kind of a robot platform when you want to change the direction immediately in any omni direction that is feasible with this kind of a thing. So why the two different designs are there? First is the left hand side black color wheel is said as a omni, and the right hand side the diagonal rollers are said as a mechanism wheel. So their name are different because the design are different, but maneuverability is like that way. Okay, whenever you want to just move the straight and sideways, means forward, backward, left and right. In that case, left one, the robot, yellow color robot is very helpful. Just because is that because you just need to rotate only one of the motors set in which direction you want to move. But whenever you want to move the diagonally exactly at 45-degree and something like that way, then the mechanism will be very easier in that case. So that's why that rulers are attached on a sideways diagonal shape. So these are the some idea which you can find on the internet also, that how the Omni will maneuver. Obviously, you need to decide that where the robot platform is heading towards and what is on a front end side. Otherwise, it's not restricted only to 4-wheel. You can also design with the 3-wheel also, and the 4-wheel and other kinds of design. There is a different design comes in action. But how do you put it in the floor, and then what direction you want to move, and that should be decided at initial state, because once it orient in a wrong direction, then it can there is a difficulty comes in a motion control. So let's say that's the left hand side forward command is given. So as you can see that the robot 2 wheels are actually the diagonal 90-degree perpendicular to the forward motion. But that means whenever I have just shown the x means the motor is not driving that wheel. Here the meaning of X means that motor is not driving in the particular wheel. It's just stopped. And whenever I show the arrow, that means the motor is driving in that direction. So direction control has been shown over here. So whenever you want to move forward, you can see that it's very easy. Just 2 wheel, left, right, and right wheel are just in a motion with the same speed. However, you need to take care that part, because if the speed are different, then also they move in different omni direction. So maintaining the same speed, and other 2 wheels are stopped, means they are stopped by their motor. And whenever you want to move the diagonally, all four wheels comes in action. That is required because you want to move the 45-degree or some angles 135-degree diagonally. So diagonal forward backward is both possible. You just need to take care which wheel particular motor, as they are connected with the DC motor. So DC motor can be rotated clockwise as well as anti-clockwise. So this shows the what are the clockwise direction of the mobile robot platform and anti-clockwise mobile robot platform. So first thing is that while designing or starting working with the mobile robot with the Omni drive wheel, you need to take care one part. That is that you need to know in which direction particular wheel is rotating as a clockwise when you give the clockwise command and when you give the anti-clockwise command. So that is first and known. And then after you just need to make the logic of wheel number 1, 2, 3, 4, and then design that to move forward, backward, diagonally, or the any direction because it's omni direction. So sideways is also possible. As I said, you stop the different motor sideways right hand side. So these wheels are in a forward, but suppose sideways left hand side, these wheels upper and bottom wheels are in a reverse direction, but these two wheels will be X, means their motor is stopped. That means what happened in that case, as you see that in a previous image, these rubber rollers help them because they are 90-degree perpendicular to the direction of that motion. So the rubber rollers are free to rotate and they helps them to rotate in the even the it is perpendicular to the surface floor, like any floor kind of the mechanism it can work. However, it is restricted to the smoother floor, and that kind of requirement is there. And the fourth one is rotatable at the same position. That means, as you can see that you change the direction of each wheel in any in particular direction of, let's say, clockwise, so it rotate on its own position. So it's not going to maneuver either forward, left, right, backward. It just rotate entirely 180-degree or 160-degree, whatever you require. It's definitely going to be rotated at the same position. So this will be easier to maneuver again this kind of a mobile robot platform in any different floor plans. That is why this kind of mobile robot route right now is accepted by many industries because they are easy to maneuver. So I'm going to show you one of the demo video regarding the this kind of same omni-wheel drive mobile robot platform from our college premises, and that you can see how does it move. Here there is no sensor attached on it, so it's not going to just consider or see any particular obstacle nearby. It may stuck with anything, but two different types of robot motion is possible by using this kind of omni wheels is possible, as you can see. So just my focus is that you concentrate over here. How does the direction is controlled of each motor of the each wheel, as well as which motor are stopped and which motor are not stopped in such a way to maneuver them in any direction. So just look at through the video. It will running at a faster speed. It rotating at the same place, clockwise, anti-clockwise, diagonally. So as you can see that it is very easier to maneuver this kind of mobile robot platform in any industrial platform. Why? Because it can rotate clockwise, anti-clockwise, or any direction from that given starting position or any ending position. So there is no restriction to maneuver them in any direction or in any particular motion control. So it will be easier, but it is only thing is that these are the special type of wheels. So it has to be restricted with the floor plan also. It has to be a smoother. Only that is the restriction. It cannot run on a muddy area or some kind of this kind of a thing because they are the rubber rollers in between the robot wheel body. Move on to that. And okay, so final point regarding these all 5 types of robots that you have designed and then you have used in your industry. But 2 things has to be considered, and industry people are also considering that whether you want to go for automated guided vehicle or autonomous mobile robots, which are the future. What is the difference that I have mentioned over here in my diagram? That is autonomous guided vehicle. As you have seen that they are the tracks or magnetic tab beneath the floor, embedded into the floor, and based on that floor plan only they can maneuver from point A to point B position like that way. So this kind of robot you may have seen in the restaurants, they are coming from that particular starting area to your table, and they are only moved by this guided path in the floor, and that is why they are restricted. So they will stop that in between if someone is coming in between them. But point is that the tracks should be defined, well defined, and then they can be. So this is possible whenever your industrial plan is well defined and you are going to use them for entire season and entire work for infinite time. But whenever you change your plan, what is my point is that whenever you modify your path or particular floor, at that time this kind of AGV will be very difficult because they you need to change entire the floor plan again to maneuver them from now A point to next new C point. So future is coming like a autonomous mobile robot, AMR. Now people are going to trackless autonomous navigation. They can travel around the people and around the obstacle, and no infrastructure change is required, and you can expand them or modify them. Still there is no restriction, only few programming is there, and they can maneuver within the your given new modified floor plan or and whatever the industrial floor plan has been given. So navigate dynamically, that is the facility of the given industrial autonomous mobile robot has been given. And that is why the people are moving towards that, because as you can see that they can maneuver anywhere considering the all the decision making of the robot platform. But first thing first is that still your floor is has been designed and your autonomy has been system has been designed. Still you need to define what kind of platform you are using. I have just gone through all different types of mobile robot only, and that different platforms. So what whichever is your application, based on that you need to decide for maneuverability of the different types of design, because you cannot change from one design to another design within that particular day time or month time, because once the platform has been designed, it can be maneuvered like the same way. That is the idea about the autonomous mobile robot, and that is the future autonomous navigation of the robotic system. So thank you very much, everyone. This is my email ID that you can see that if you have any question, you can ask me, or you can just mail me anytime, any way, if you have the doubt in regarding the mobile robot types. If you have any question, you can ask. Different configuration. Omnidirection, yes. Omnidirection has a omni wheel, that is a normal one. And macadam wheel has a different design. You cannot use both as simultaneously. And obviously, once you are the four-wheel design or three-wheel design, that doesn't matter. But in a macadam, it has to be a four-wheel design because the rubber rollers are diagonal. So you can easily move the diagonally. The robot can easily go 45 degree. But point is that even they can move the forward, backward, left and right. The configuration are only related to the omni is such that anywhere in the mobile robot platform you can choose the direction and can move on with that. So that is a particular idea that you need to give the mobile robot with the different types of special type. I can say this is a special type of wheels, and the traction is the issue. Yes, as I said, this is a special type of wheel, and as you said that traction is, as I said that the floor plan has to be well defined whenever you are going to use that either in an industry or even a project or even on your office or college campus, whenever the floor plan has to be designed, because they have the traction issue. If there are not smooth surfaces and the rubber over when stuck in between the in a muddy area or something like that way, then they cannot maneuver easily in that direction what you want to move on. So that's obviously that's a one kind of disadvantage you can say for this kind of platform. But otherwise, for turning purpose in any direction, omni or mechanism, both one drive wheels is very best. Autonomous mobile robot can move around unknown environments without. Okay. Yes, autonomous robot can you move into unknown environment without a prior known map using an IMU, but you still required other sensors also. It's not only depend on only the IMU. You can restrict them to maneuver within the smallest indoor area. But point is that once you give the IMU based only information or data to maneuver, then they have the restriction or limitation in the motion control within that area. So your A point, B point will be nearby in that case. But if you want to move the autonomous robots in the entire industry, so that is why, as you said in some of the images, they require the LiDAR and other distance sensor, because they need to bypass somewhere some obstacles and some human being, anyone, because they cannot stuck with anything in easily without giving the information. So they are automated, as the word says, autonomous. So they are fully automated. There is no human intervention between them, and he has to decide by itself that whether I have to move in a particular, whether robot has to move in a particular direction or not, as per the requirement. But main task is that it has to navigate within the floor plan from given start position, source position to destination position. But the path is not defined. That is AMR. Okay, the path is not all defined. You need to require the mapping of your known map. Unknown environment is little bit difficult right now. So all research are going on that. And as I said that my research topic in the PhD is also the autonomous unmanned vehicle for the unknown environment. So I'm going on a research, and once I come out with the solution, definitely I would like to share. So that is why I have given you the email ID, and you can share your ideas also. An algorithm made for mobile robot with 4 wheels, is it easily scalable for different number of wheels? No, it is not that much easier, because as you reduce the number of wheels, let's say from 4 to 3 or 3 to 4, your direction control has to be defined initially. Okay, different size matters obviously, but size is about the speed control. Okay, I'm talking about the number of wheels, not the different size. Size matters only for your speed control from moving one point to another point, the size of the wheel or motor torque and everything. But here my point is that different number of wheels, if your configuration is being changed, let's say I'm using omni wheels for some motion of, let's say in industrial from point A to point B using the 4-wheel omni, and suddenly I modified my robot platform for 3-wheel, then also obviously my algorithm inside that robot has to be changed, because for moving forward and backward and left side for the 3-wheel is a different things, and 4 wheels is a different things. So you need to take care at initial stage that how you, what kind of wheel numbers are you using for a particular omni wheel robot. 4-wheel mechanism. The track was most probably not 100% flat, and that's why one of the wheel was not completely in contact with the floor. How can such problems be avoided with the wheel mechanism drives? Obviously, I can understand, as I said, because this is the most difficulty everyone has found, even in the competition, that whenever people are using mostly in the competition, the mechanism type wheel or omni wheel, and in that case, that problem is always remaining the smooth surface regarding that. So I suggest that the traction can be implemented within that if your robot's weight has been has been increased from heavier robots. We have touch with the ground, and then that can be little bit avoid the problem that you may have faced. But totally, as I say, totally uneven surface cannot be useful for Omni or even the Machina, totally uneven. It has to be a little bit flat or smoother. However, some slant and some uneven surfaces a little bit are there. But for that, I can suggest that use the heavier robots so that it can provide the weight of the robots towards the floor. And because of that, the contact remain of the wheel towards the floor will always on the time. But as I said, the Omni will always require the feedback, whether it's a particular motor is rotating wheel freely or just in one particular direction. So that kind of feedback is also required. I'm not saying only the increase the weight, but you need to increase the particular what you can say the feedback system in which the whether a particular robot one wheel is keep the particular motion. That means it's not moving the robot, but it's just rotating faster. So that kind of encoder based what you can say sensors are available. You must need to use that. Can we integrate the Google Maps in robot to understand and move around? Yes, it is only for restricted in outdoor, first of all, because I have tried with the indoor and the signal matters, and that least number of satellites has to be there. 4 number of satellites must be there, and otherwise you cannot maneuver within that. So if there are the high-rise building nearby or some trees are there, then also you have some kind of restriction over there, and you may cannot move there because the data will be there, but it may fluctuate within that time. So you cannot judge about the accurate position of the GPS, whether you want to move from one point to another point in the outhouse floor or outdoor floors like that way. So obviously GPS can work with that, Google Map integrated. However, some kind of algorithm is required, but it only for open sky area that I can suggest that, not for nearby buildings or nearby trees are there. Then and at least number of satellites must be detected as a four. If you detect three satellites nearby and above, then there is a restriction in the getting the clear data. But if it is a four and more than four, then it will be the definitely the accurate data will be there. Okay, so I hope I have cleared your all the queries, and you are satisfied with the answers.
Yes. Thank you very much, sir. Professor Vishal Vaidya, sir. A wonderfully and very knowledgeable information shared with us about mobile robot drivetrain, mobile robot omni drivetrain, automobile robots, automatic guided vehicles, and lots many query solved by this, sir. Now, one more experts we have with us from the team of Dr. Nagendra Gajjar, sirs. So I welcome Dr. Jatin Kumar Dave, sir, on behalf of eInfochip and IESA Gujarat section. Dr. Jatin Kumar Dave is working as an associate professor in mechanical engineering department since 2005. He has an experience of more than 16 years in the field of teaching, research, and industry. He obtained the mechanical engineering degree in 1999 and ME CAD/CAM degree in 2002 respectively from Gujarat University. Dr. Dave obtained PhD degree from Nirma University in 2016. He has published more than 30 research papers in international journal and international conferences in the area of stress analysis of composite material, finite element analysis, machine design, CAD and robotics. He is involved in major project funded by Coast. He completed 3 minor research projects funded by Nirma University. He has guided more than 20 PG dissertation. Dr. Jatin Kumar Dave is a reviewer of international referred journal in the area of stress analysis, finite element analysis, and etc. His research interests include a stress analysis, finite element analysis, robotics, and CAD. So again, I welcome Dr. Jatin Kumar Dave, sir.
Yeah, good morning to all of you, and thank you for inviting me on this session. So, as the topic is case studies and application, here I try to gather all the technical content in such a way that even if you are a beginner, yeah, you will be able to know when to start. Okay, what kind of mathematics are required, uh, what kind of programming you can involve during the solution of the all the equations. And also some of the applications of the use of software also I accommodate so that you can very easily know how to start with the kinematics, dynamics, design, and further already some topics are already covered, the electronics aspect, interfacing, etc. So that will help you to start from the scratch. So that was the whole purpose of this my lecture. So uh, this is my outline of presentation. So try to cover some of the aspect of quadruped robot, which is the area of legged robot. So this is covering the very fundamental of the leg motion, how to define the walking pattern, what kind of positions concept can be implemented, and some of the programming aspect and simulation. Also, I will try to cover the bipedal robot, very basic aspect of bipedal robot in my third subsequent topic. Some of the work initiated in the area of climbing robot, so that also I will try to cover, in which I try to cover the mechanism based leg design and also some of the aspect of wall climbing robot. Some solution on track wheel concept, cleaning robot, and some of the other application I will try to cover. As I told you, my purpose is to try give you the concept of a design from the scratch. And basically, my strength is mechanical engineering, so I will try to cover kinematics, dynamics, and design aspect. Okay, so that you can design your own robot in a from the scratch and with the concept which whatever given to you, and it will be helpful to come out with the best design. Okay, so let me start. Now you have gone through so many classification in these 2 days, and you are fully aware with the kind of a robot which can be implemented nowadays in societal application, industry applications, defense, etc. Specific to legged robot, from these two initial classification, manipulator and mobile robot, where mobile robot have again major classification under the wheel, track robot and leg robot. Leg robot also we can see that the classification can be two-leg robot, which is a popularly known as a bipedal robot. Quadruped robot are very popular in industry. Many companies like Boston Dynamics and many other companies have already made beautiful robots working commercially. Some of the work is already done in hexapedal robot, which is a 6-leg robot and having the more stability aspect. Octapod also being used by researcher in many of the applications. And we can see that looking to terrain adaptability, energy efficiency, and maneuverability on the rough terrain, legged robot are preferred many times over a wheeled robot. But of course, it costs you mathematical complications, complex equation, very complicated control aspect, etc. But it depends on your application and requirement, what kind of robot to be implemented. You can also go through many researchers who are pioneer in the design of this kind of a robot. Maggie was one of the researcher, which I didn't mention here, but this Hirose is again one more pioneer in the quadruped robot. And one of the statement you can find in his research work, that is quadruped robot is the best form of legged robot from the aspect of stability, control, difficulty, and manufacturing cost. And that's why it is popular nowadays. And you can see the very beautiful robot made by NASA and Boston Dynamics. This table shows you comparison between legged robot. The parameters taken here is maneuverability, stability, load carrying capacity, and control simplicity. Okay, so two-legged robot, bipedal robots, we can see that it's imitate a human walking motion. So maneuverability will be very good. But of course, we experience that even if we have some kind of a sickness or anything, we face difficulty in walking. Okay, so you can imagine that how much complexity required, okay, to implement that kind of a control in a bipedal robot. Load carrying capacity, of course, will be less due to this dynamic complexity, and control simplicity will also be very less because we have to continuously walk, and dynamic stability is expected from the design. Now, if you go to 8-legged robot or 6-legged hexapedal robot, maneuverability always will be less because there are so many legs. And while orienting its body or walking over some kind of unknown terrain or stairs, you need to take a control of all the legs together. Simultaneous motions are required. But of course, stability and load carrying capacity will be more. Okay, so we can find the more star here in these two parameters. Control always difficult because number of legs are more. While you will find this 4-legged robot, quadruped robot will be in between all these other 3 kind of a robot. Okay, so maneuverability you can achieve some sort of simplicity and all kind of orientations are possible. Stability will be slightly less compared to 6-leg and 8-leg robot because you have only 4 leg, and many times there is a issue with the center of gravity and the walking pattern. Load carrying capacity will be limited because you have only 4 legs and 4 point will be in touch with the ground. So that going to be limit your load carrying capacity. Control simplicity will be slightly achievable, okay, because you have 4 leg, and if you have symmetric walking pattern, okay, then your simplicity in the control can be achieved. Again, if you want to go into domain, okay, what kind of research area you can explore in term more general in a legged robot, okay, not only limited to quadruped robot. So you can start with the understanding the walking of animals. This terminology we will understand in our discussion subsequent slides. So like gaits are walking pattern. How do you sequence your steps? Okay, that is defined as a gait. So many variety of gaits are implemented like a continuous and discontinuous that we'll see in definition in our upcoming slides. People are also working in having the all kind of orientation while walking. So they call it as omnidirectional. People also implement body sway motion while walking so that stability is achieved always. People also work in the area when if any legs are not working, okay, then they call as a fault tolerance gaits. So even with the 3 leg, robot can work properly and you can retrieve your robot for the maintenance purpose. You will also find research in the slope and straight climbing. And another issue is the control architecture. What kind of control and nowadays how to implement AI machine learning, okay, to work in kind of a uneven terrain or more complex working pattern you can implement with this kind of a implementation. Okay, so these are all research area you can explore later on if you are interested in the legged robot. Now coming to basic definitions here. See, this sketch will help you to understand the top view of a quadruped robot, specifically looking to the workspace of a leg. So this each rectangle, leg 1, leg 2, leg 3 and leg 4 shows the workspace of a leg. So this is provide you coordinates on which you are able to put your foot tip. Okay, these all small circles, they are the foot tip of a leg of the quadruped robot. And on these points, you are able to move your leg so that you are able to walk. Okay. Now in this sketch, again, we have shown the coordinate system at the center. So this is the your global origin, or you can say the origin of the entire robot here will be located mostly in the at the center of gravity. Okay, and here in this case, it is the center of the robot. So gait, as I told you, it's a walking pattern. How the sequence of the steps to be followed, that is called a gait pattern. Now see in this sketch, triangle is shown, okay, with the 3 legs which are on the support of the ground, and one leg 4 is shown which is moving right now with the this arrow shows the motion of this leg 4. So you will have a triangle formed by the foot tip which are on the support on the ground, and your center of gravity should remain inside this triangle so that you will achieve stability always. So this is called statically stable gait. Okay, so when your center of gravity will be inside this support polygon, okay, the polygon which formed by the foot tip with the support on the ground, then you will not have an issue of the topple of the robot and you will achieve stability while walking. So mostly people are trying to achieve this static stability while implementing the gait pattern. And in this, suppose you have the symmetric sequence of the step always, okay, then it is called as a periodic gait. Okay, the robot follows the same event sequence in each of the cycle. Sometimes looking at the change in the terrain, change in the ground environment, you may also design a gait sequence which is adaptable. So you may call that as a aperiodic or free gait. So more complex control and more AI and machine learning algorithm to be implemented in this case. So it changes parameter in each cycle as per the terrain condition. Further going into depth of this kind of a gait pattern, classification and terminology. Suppose you keep moving your body along with the leg, then also it is called a continuous gait. Okay, so robot moves continuously similar to the animals. While suppose you separate your leg motion and body motion. Okay, suppose leg 1 is move forward, then you move your body. Again leg 2 move forward, then you move body. So this is a discontinuous motion separate with the body as well as leg. So this intermittent body motion is performed instead of continuous motion. That is called as a discontinuous gait. The body moves only when 4 legs are in the leg on the ground. That is the statically stable condition, and leg swings take place when the body is steady. Further, in this discontinuous gait, you can also have a body motion after the one cycle, that is one phase, 2 times in between the cycle, that is 2 phase, and 4 times in between the cycle, which is 4 phase. So let us go into detail of this 1, 2, and 4 phase. Normally, people who are working the legged robot, they will first determine this kind of a your gait diagram. Okay, gait diagram shows the motion of the leg or foreleg with the time. Suppose here the time is shown as a 12 second, which is a cycle time for me, and I will show the motion of the leg 1 to leg 4 during this 12 second. So here it is seen that leg 4 is started as a first. So 1 second to 3 second is the leg motion of the leg number 4. Then you can see that 3 to 6 second is the motion of the leg number 2. Then subsequently 6 to 9 second is the leg motion of the leg number 3, and then leg number 4. So this shows the your gait diagram, which shows the distribution of your cycle time in between the motion of the leg 1 to leg 4. Also shows the sequence of the leg to be followed. Sequence here is leg number 4, then leg 2, then leg 3, and leg 1. 4, 2, 3, 1. Okay. Now with this gait diagram, the classification of 1, 2, and 4 phase is shown here. Now, as it name indicate, one phase, so body motion takes place after each cycle. Okay, so here's the gait diagram for leg motion is shown here. So leg 3 first, then leg 4, then leg 2, and then leg 1. After this, the gray area shows the body motion. So for remaining 4 seconds, your body motion will takes place, and this cycle will repeat. But in the 2 phase, after motion of each 2 leg, the body motion takes place. So here it is shown that leg 4 motion followed by leg 2 motion, and then body motion shows again leg 3 and leg 1, and again body motion shows here. Okay, and similarly in 4 phase, after the motion of each leg, body motion takes place. So this third diagram shows the 4 phase diagram. So you have to decide as per your convenience which kind of a body motion you want to implement. Like say in this example, 2 phase discontinuous gait is shown here with the body motion. Okay, so let's say we started with the motion of leg number 4 first. So in this rectangle, 4 leg in transfer on the left side of this PPT. The leg 4 currently is in motion, and other 3 leg will be on the ground, and we can see that CG is inside this support polygon. After that, leg 2 will take in motion, will come in the motion, and other 3 leg will be on the ground. So that is the leg 2 in transfer. After that, as the concept is 2 phase, then body motion takes place. Okay, so body will move slightly further. Body can move in any one direction, or it can be moved in a combination of XY coordinate. Okay, that depends on your programming. Further, leg 3 motion takes place, then leg 1 motion takes place. Again, will body move in a forward motion like this. So this way, the programming you have to take care which kind of the 2 phase, 1 phase, or 4 phase you want to implement. Now the question is, how can you understand whether my motion will be stable or not? And for that, people have used stability margin as a terminology. So stability margin shows the position of center of gravity. Now, as the statically stable gait, we defined that the center of gravity must remain inside the foot polygon, the polygon formed by the foot tip, which are on the ground right now. So you will achieve statically stable gait pattern always when your center of gravity remain always in the foot polygon. Okay, so it is statically stable stability margin, which is short called as a SM. Now here we have 2 kind of stability margin. We can see from the figure that it is a measure of the shortest distance from the boundary of the foot polygon. Suppose these points are shows the foot tip which are on the ground right now, and perpendicular distance from the CG is the SM. Okay, stability margin. But people also utilize the longitudinal distance. Okay, you can see that straight line here, horizontal line LSM, which is this longitudinal distance of the CG from the support, any of this support boundary, or you can take minimum distance LSM from all these 4 support boundary. So it is a longitudinal stability margin. It can come as the distance of the projection of CG from the nearest support boundary in the longitudinal direction. So both you can go on comparing during your motion cycle, and you are able to analyze the stability of the robot. If the distance falls out of the margin, then your robot walking may not be stable. Otherwise, it is going to be stable. Some more terminology like duty factor. So fraction of the cycle for which the leg is on the ground. Okay. For regular gait, value of duty factor will be same for OR leg. Leg phase is a normalized time by which placement of leg I on the ground leg behind the placement of leg 1. Suppose leg 1 is your reference. Then you will get the time of each of other 3 leg, and you will divide the time of leg 1, which is your leg phase. Leg stroke is a distance which a foot is moved relative to a body during the support phase. Stroke pitch, it's a distance between the stroke center of the adjacent leg. And stride is a distance traveled by center of gravity of robot along one locomotion cycle. Okay, so stride is the total body motion, robot motion in one cycle. Stroke pitch is the distance of adjacent leg, that is leg movement. Okay. Now let's go to some basics of geometric modeling, the coordinate system assignment, and how can we come out with the kinematic equations, etc. You can provide the symbolic variables like L shows the body length, W shows the body width. Okay, then Rx and Ry. Okay, these are the your workspace distances. Rx will be the distance of the workspace in X direction. Ri is the distance of the workspace in the Y direction. So Rx, Ry provide the leg workspace indication, whereas L and W provide the body size. Further, we are aware that it's a multi-body dynamics. So we use coordinate system, okay, to analyze the position, velocity, acceleration, etc. And for that, you need to assign coordinate system. So I is the inertial frame, which is located at the center of gravity of the robot. Normally, if it is symmetric design, then center will be the inertial frame, global coordinate system. Correct? Then subsequently, you will have coordinate system for each and every joint of the leg. So here for one leg, it is shown here. Z1, Z2, Z3. These are the body joint motion axis, and link 1 and link 2. So this diagram shows the key point for gait planning. Okay, suppose we have leg workspace indicated by Rx, Ry, and you can divide Rx, Ry into number of points. Like say in one phase, here it is shown as a 4 point. So A1, A2, A3, A4 are the 4 points. 2 phase, it is shown as a B1, B2, B3, 3 points. 4, we have divided this workspace into 5 points, C1 to C5, like this. So this point will help you to determine the coordinates for each and every leg motion. So let's go into detail of this. Okay, suppose this table shows the event sequence of one phase discontinuous gait. See, remember our point will be A1, A2, A3, and A4 in one phase cycle. So let's say we start with the 0 second. 6 second is the time given for a leg, okay, to move forward. So let's say event is starting of the leg number 3 as 3. So leg 3 will move from A1 to A3, whereas other leg are on the ground and points are A1, A2, okay. This is so the leg 1 to leg 2 and leg 4. So you will have workspace similar to this for each leg, and A1, A2, A3 are the point of the workspace. So A1 to A3 is the motion of the leg number 3 in event number 1. Then event number of leg number 4 will start. So leg number 4 will move from A2 to point number A4, whereas other point will remain on the ground. Similarly, then leg number 2 will start A1 to A3. After that, leg number 1 will start A2 to A4. Now, as it is a one phase, so after the completion of leg motion of all 4 leg motion, your body move forward. Okay, so body move forward and all the 4 leg will change the position to subsequent adjacent point. And this cycle repeats after that. Now let's go to 2 phase. So from the 2 phase, we know that body has to move 2 times in between the cycle. So let's say we start with leg number 4. Leg number 4 will move from B1 to B3 point. Then leg number 2 move from B1 to B3 point. After that, body motion takes place. So all leg point will change. Again, remaining 2 leg, which is leg number 3 and leg number 1 will takes place motion. And again, body will move forward. Okay, so you will have coordinates each time, and these coordinates will help you to identify the angle of a joint. Okay, let us see what is that. This table shows the 4-phase discontinuous gates. Again, now from the previous 2 table, I hope you are able to understand how the motion will takes place. Name indicates 4-phase. So after motion of each leg, body motion will takes place. Okay, so let's say leg number 4 motion, then again body motion, leg number 2 again body motion, and then follow in a similar manner. That means if you go for 1 phase, 2 phase, and 4 phase, your number of points will be increasing. And each time you have to do computational to find out the joint angle. Okay, so let's go into detail of this. So here example taken is very simple example. It's a only 2 degree of freedom leg. So very simple to understand. Also kinematic equations are very simple, easy to understand by all of you. All branches can very easily understand this concept. We require this inertial frame, global coordinate system, and the coordinate system for each joint. Okay, so here only 2 joints we have. So theta1, theta2 represent joint angle for these 2 joints, and point number P represent that our point. Okay, that point A1, A2, A3, A4 in 1 phase, B1 to B3 in 2 phase, C1 to C5 in 4 phase. Okay, so this point will be represented by P here. Now you need to know the coordinate transformation when we are working in the domain of robotics. So this 4 transformation matrix T1, T2, T3, T4. This shows the coordinate frame location from the center of gravity. That means from the global coordinate system. So as we indicated distance L and W, okay, in our previous diagram, that indicates the length of a body of the robot and width of a body of the robot. Okay, so this shows the translation, that is your position of the each leg from the center of gravity and orientation of each leg from the center of gravity. So this will help you to transfer your coordinate with the CG of the robot after each cycle. Okay, always it will try to map the leg coordinate system with the coordinate system of the center of gravity with the help of all these 4 metrics. Okay, now in previous table, we have find out our points and the sequence of the motion of the points, like say from point A1 to A4 in 1 phase, B1 to B3 in 2 phase, C1 to C5 in 4 phase, like this. So this point you can represent it here. See, this dotted line at the bottom shows the trajectory. Okay, suppose you initially this 1D, 2D, 3D, 4D, and 5D. Okay, these are the points on the ground. And when the leg move upward, okay, it shows the 1U, 2U, 3U, 4U, and 5U points when leg is in a swing phase. That means while leg is moving. Okay, so only this height will be changing, XY coordinates remain same. Barabar? So we have value of all these points. Okay, from the coordinate XY, we are able to calculate it. And this will work as an input to find out what value of angle to require so that our joints will be able to move. Joints will be able to rotate. And then this body will be able to move forward in the direction of a travel. So all these points 1D to 5D and 1U to 5U work as a trajectory for us. And we also know time. Okay, from the table we assign a value of time required to accomplish the motion from one point to another point. Okay, that is also known to us. So as this is the only 2 link, 2 degree of freedom, 2 joints robot. So kinematics equation will be very simple. And from the arithmetic, you are able to understand what will be the value of xy if we know value of theta1 and theta2. Or we can form the equation, which is called a forward kinematics, to find out the equation for x coordinate and to find out equation for a y coordinate. And from this equation, while solving this equation, we are able to form the inverse kinematic solution for getting the value of joint angle theta1 and value of theta2. So as from the table, our input is coordinate xy, length of links are known to us, okay, because we know the size of the robot, and from the available environment, we are able to decide the range of the dimension of the robot. Okay, so that is known to us. Xy will work as input. And how to get xy? Okay, this is working as a xy. Our points 1D to 5D and 1U to 5. This provide you value of xy. Okay. So this is working as an input here to find out the theta 2, and based on the theta 2, we are able to find out theta 1. So this is working as a inverse kinematics, and value of joint angle theta 1, theta 2 will be always available to us to move the revolute joint of a link and subsequently move the body of the robot. So for example, we have defined this terminology earlier. Duty factor, so labeled as a beta here, 0.75 is taken. Leg stroke, 14 centimeter is taken here. Leg swing is defined as a 4231. Okay, the gate pattern taken as a 4231, which is popularly labeled as a wave gate. Leg phase, so as we know that leg phase, leg 1 is taken as a reference and the ratio of other 3 leg will be taken here. 4231 is our sequence, so 4.25, then 0.5 for leg number 2, 0.75 for leg number 3, and with reference to leg number 1. Stride length is 14 and cycle time taken as a 12 seconds. Lambda is a factor defined by R divided by beta, which comes to 18.67. Okay, so let's go further. Now, how to implement this? Okay, so you can initially you have to work on the paper, okay, to formulate your equations, forward kinematic solution. Okay, then you need to achieve the inverse kinematic solution. Then you know what kind of coordinates value are required. So from the table, you are able to get value of xy. Okay, for any of the selected phase, either 1 phase, 2 phase, or 4 phase. And then you put everything in an algorithm form. Okay, software can be anything like MATLAB, Python, or any other can be utilized as per your convenience, but algorithm is required. So here MATLAB environment is taken to carry out the simulation, and we know that MATLAB is having a strong robotics toolbox. So we will put everything this in robotics toolbox and we do the coding here. So representation of the robot in the form of a rigid body tree. From coordinates and solution of theta 1, theta 2, from inverse kinematics, we know what is the initial value of joint and what is the final value of a joint for each theta 1, theta 2. Then from the table, key points, that is xy value, is also known to us for each time. Okay, starting from 0 second to the 12 second, we are knowing what is the value of xy coordinates at each leg and at each sequence. Okay. Then using inverse kinematics, by providing input of xy, we are able to get the value of theta 1, theta 2 for each time interval. Okay. So remember, we are getting the trajectory here. Trajectory means your value of position with respect to time. Okay. So that is what we call as a trajectory line. And this we have to do for all 4 legs. Okay. And time is known. Already in the table, we have distributed time between each leg sequence. Okay. So it is known to us. Then use this robotics toolbox. We may also require the Simulink model, okay, because programming will provide the value of angle for each time interval, and then Simulink will help us to put everything in a block diagram and then solving for entire motion of the robot. Results will be acquired, and then you can do analysis as per your convenience. You can compare result between different cycles, different phase working pattern, and you are able to get the best out of it. So let us see. Okay, so here the live coding I may not be able to show you, but a snapshot I have taken for your information. Let me. Okay, so we will see if time is available, snapshot, but this kind of output you will get. So see, we have implemented X motion, barabar. So from here we can see that other two distant coordinates remain constant. Okay, only this blue line shows the X distance. Okay, so that is the only changing here, whereas Y and torso height remain constant. Also, we are not going upward and downward, so Z coordinate is meaningless here. Only X coordinate is important to us. This diagram shows the angular position variation, like say leg 1 angle, okay, which is a hip angle. Okay, and then hip 2 angular velocity and hip leg 1 hip angular position. So angular position and angular velocity is plotted here. you can see that symmetric pattern is followed, okay, for both angular position as well as angular velocity, which indicates that your motion is symmetric, followed the sequence of the gate diagram which is designed by you. Also not having variation, so that smooth motion of the robot will be achieved while completing the entire cycle. Okay, so that is what the gist of this analysis. So we try to implement with a very simple fabricating initial simple robot. Let us see. So we calculated all this in a MATLAB, and then we interface the hardware here, and we implemented the angle value, and you can see that statically stable motion is achieved here. Okay, let's move forward. This particular robot is made for 3 degree of freedom leg. Okay, so each leg is having 3 degree of freedom. There are 3 joints. You can see that here we have vertical motion, then subsequently the joint number 2, horizontal axis here, and then joint number 3. So 3-legged motion. We face difficulty because of the size and payload capacity, and all, of course, your selection of the actuators, etc., will also play a major role. Also, design of electronics, the way of working, the soldering pattern, everything matters a lot here. So if you miss anything in between, then you may not achieve proper motion. Okay, so we are working on this right now. Let's see. Here also we try to implement body sway motion. Okay, so you can see that body is also moving in a zigzag manner. See, now it is going in a right side. Again, 2 subsequent legs are for move forward. Then again, body goes in a left side. So body sway motion helps in maintaining stability. See, you will get a beautiful robot, a beautiful design by many research institute like Boston Dynamics. But always there is a scope of research always going to be there, because we may not know what are the limitations they face. So only by doing research and thorough brainstorming, we are able to know what kind of limitations are imposed on all these commercially available robots. They looks like, okay, very good way in moving. Okay, but when you start your research, you will be able to get the research scope always. And that's what we are doing, okay, right now. See, this is one of the commercial name Spot, okay, which is shown in this figure right now. Navigates terrain, automate routine, inspection task, etc. So camera implementation, the obstacle avoidance sensors will play also major role here. Not only the kinematics, remote inspection capability. Suppose you have any kind of a cyber physical system or connectivity, you are able to also get the video feed on your computer or tablet. You can also implement many kind of sensors like visual sensor, thermal imaging sensor, like say you want to implement these robots in nuclear inspection site or some temperature important site, etc. Autonomously record sample of for analysis by third party, acoustic, etc. Okay, so variety of application can be possible. This was the motion here. You can see that body remains inclined, okay, that almost parallel to the slope of the stair. Sometimes while okay, doing societal application or industrial application, when carrying a payload, we may not allow, okay, body to be inclined. So you may think, okay, how to maintain body horizontal. You have already worked on that. Here in this presentation, I have not kept all this research aspect. My purpose is to provide you the case study here, okay, and of course could be simple for you. So your kinematics is the first step, okay, then control will come in picture. You can see that complex control implemented here. So that was the task of your other team members, which are belongs to instrumentation and electronics. It's an entire teamwork, okay, it's not a work of one man. You need a team. Other case study which I would like to show, okay, mainly structural climbing robot. So this area is also very important, okay, looking to the manpower requirement, safety of the manpower, reducing repetitive nature, and also providing assistance to the manpower which are climbing on a variety of structure. You can take a case of tree climbing robot where people are going in a very height, okay, to pluck some of the fruits like coconut, etc. People also go to height to carry out some maintenance work. Frequently, people cannot go up and down, okay. So if you devise some kind of a robot which can go upward, provide some assistance to the human, then it will be very helpful to the society. Okay, so this is a kind of a introduction here which provides you motivation to work in this area. Risking human lives is the foremost motivation for us. Example taken here is the telecom market. Okay, so many tasks are predefined. Okay, you need to follow step for carry out maintenance, and we can take help of automation and robotics to carry out all these tasks. So if you go to do a research in finding what kind of climbing robot available, okay, you will get a lot of variety. People all over the world, people are working here. Okay, so you may get a lot of variety. But climbing robot is very challenging. Okay, so you will always find a research gap, and you can define your own objective, and you can propose something which can be helpful to the people. You will find pole climbing robot, okay, with a variety of gripper also. Gripper is very important here, okay, because that is the only the end effector or a tool which is remain in contact either with the wall or with the stair or with the tree, whatever application you take, or a pipe, etc. So your major challenge here is to design a gripper. Okay, so yesterday you have come across the gripper application. Okay, these are all different kind of gripper shown here. This is a wall climbing robot here, which can use many kind of a adhesion device like vacuum or magnetic or a gripper kind of a device or any other. Column climbing robot is shown here. Okay, so your gripper will work as a hand which can always in a contact with the column. This kind of gripper also very popular, which can work as a universal gripper. So which it is helpful in a wall as well as on a column. Okay, so the problem statement is shown here. Particularly, as I told you, the concept taken here is to climb on a ladder, which will help to do some kind of a repetitive work, okay, for climbing a ladder of the telecom tower. And you are very well aware that climbing a telecom tower is very difficult, risking human lives. Injury takes place. Carnivorous birds may be present on the height. Weather conditions, electric shocks, burning of the telecom tower, which take your very costly instrument. Okay, so it's very important for us to come out with some kind of robotic application. See, this figure shows help you to understand different kind of telecom tower. Okay, so you will find variety of telecom tower, but of course you will come out with the stair design always. You will also get a standard, okay, of telecom tower, from this information we have initialized with one kind of a one of the climbing robot. Again, it's based on the quadruped robot design, but now the purpose is to climb a ladder of the tower. Okay, so this figure will help you to understand the concept here. Components are listed here, which of course we have not successfully so far, but we try to implement in our study. So initially we have taken only few components because concept implementers is very important in our initial phase. So our purpose is to design gripper. As I told you, it is important. Other component, okay, can be taken care, but gripper design is important. Now see again, from a mechanical guy, I always start with mathematical modeling. Okay, and from the basics of robotics, if you study robotics, then you know DS table, okay, Danavet and Hartenberg table. Danavet and Hartenberg are the very important researcher in the 20th century. They provide a way of analyzing a motion in a 3 dimension. Okay, so coordinate system assignment is shown here. The parameters are shown in this table. This help you to come out with the mathematical model, porokinematic model. Okay. Now see, this robot is having a 3 joints, so your mathematical model will be in terms of a matrix. And again, our ultimate goal is to know what is XY location. Okay. So ultimate matrix you will find in terms of XY location here. See, location of point number 1, point number 2, point number 3. And it is a function of your all the 3 joint angle, theta 1, theta 2, and theta 3. So this figure help you to know what kind of trajectory. Suppose I rotate this joint to pick up the to grasp the ladder. Then this joint will move completely like this. So that it will come out and it will grab the ladder of the stair. It grabs the ladder on the stair. Then subsequent motion of the joint number 2 and joint number 1. Now the important is to know what is value of joint angle always, because points are working as input. In previous example also I show you that XY locations are input to us. Our interest is to know what is theta 1, theta 2 and theta 3, so that this is working as input in our controller and subsequently it will try to run an actuator for us. So by going through inverse kinematics concept, we are able to know what is the equation of a theta 2. Here also you can see that x2y2 is the input here. Then subsequently moving from theta 2, you are able to know the solution of theta 1 and subsequently you are able to get the value of theta 3. So once you know equation to solve theta 2, theta 1 and theta 3, it is very easy to convert your equation in an algorithm form, write a program, run the program, get the value of angle, and then just interface your device to actuate your servo motors. So this is the ultimate concept that we come out here. And you can see that a stair is designed with the standards for the telecom tower. Gripper is also designed. Red color shows the gripper here. And other toolings will help in the motion of this robot. We also tried to implement by some plastic component initially. So let me show you this. Of course, stability is a challenging area. You can see that the robot is not as stable. See, it is completely moving out of the plane. Sometimes it's also lose the contact from the stair and falls down. So come out with the contact analysis, the finding the friction force, the slip model is also important here. You need to see the equilibrium, that is stability, dynamic stability will play a role here because your center of gravity always move out of the plane of the foot tip. That means dynamic stability is important here. So these are all research avenue for us. We are working on right now on this. This was the simulation of other kind of a robot. You can see that all legs come one by one and it's moving upward by grasping the ladder. See, other research area is pipe climber robot. You will find lot of tanks, very huge tanks, very maybe very huge in height, also depth. If it is a underground tanks for storage of maybe normal liquid, industrial liquids, or very hazardous liquid. So always problem for human to carry out maintenance, to carry out inspection, to go inside and just see what is the condition of our devices, etc. And you will find lot of company not only in world, in India as well as in Gujarat. So this gridboard company is in Gujarat, Ahmedabad, nearby Ahmedabad, which is in the area of the fabricating robot like this. So one of the application of this company is the pipe climber. It is designed for magnetic surface. So you can see that there are the ferrous material used here. Magnetic pipe surface with a payload up to 5 kg. And most extreme temperature surface conditions are taken care here. It is mainly to have the surface inspection, weld inspection, painting, coating, grinding, etc. They are using the geared motor, the pedometer, then IMU sensor, track the motion, etc. And also ultrasonic sensors to measure the tube thickness, report in time, real time based compute, etc. So many other concept we can implement with reference to the measurement, data transfer, etc. as per your application. But coming out with the concept is important for us. Let's see its application in video. So you can see that they have implemented motion in a very sophisticated manner. Of course, ferrous material. So your adhesion always ensure that robot remains in touch with the pipe. Otherwise, you need some kind of addition technique. Like suppose if you take a wall, okay, then you can use centrifugal effect, you can use vacuum effect, you can use a suction cup, vacuum cup, etc. Okay, suction cup for a glass kind of a wall is very simple, but when it is a normal wall, then it will be difficult. You need to ensure vacuum always. See, this table shows other kind of climbing robot, particularly wall climbing. Okay, so people see it's a suction cup here, utilize here. Then a caterpillar kind of a design. So all these are okay, the suction device. Okay, of course it's not having any payload capacity, but little bit of inspection and measurement you can always implement. This was the propeller kind of a design. So in the center they have a propeller which create a vacuum for you. Okay, and always it ensures the contact with the wall. This shows the wall climber, 4-leg kind of a robot. Also, see, we need either adhesion in the leg of the robot or some kind of a suction device here in the center of the robot. This shows the magnetic adhesion here. See, one of the case study I would like to take here is the simple design of a wall climbing robot. Of course, equation, because mathematics will come in the role. Okay, so equation will be very difficult for you, but I will help you to make you understand how to begin. Okay, as I'm dealing with a case study. See, always coordinate systems are required. Okay, whether you work in an industrial manipulator robot or a mobile robot. Again, mobile robot, either you work in a leg robot or a wheel robot. Coordinate system always required to map your coordinate with the global coordinate system to the coordinate system of the wheel or a leg, and it will be changing always. Okay, so you need the solution of a forward kinematics, and you also need a dynamic equation to understand what is the variation of a torque in each wheel. Also, the requirement of velocity and acceleration of entire robot. And popular formulation is mathematical equation is Euler-Lagrangian formulation, which help you to arrive at the dynamic model of the robot, and that will ultimately provide you the torque variation. Okay, so the coordinate system is shown here in this figure, and now I will show you the equations directly how this Euler-Lagrangian formulation is implemented. Okay, so see, this Euler-Lagrangian equations require kinetic energy and potential energy. Kinetic energy is combining both linear motion as well as angular motion. So angular motion will be in the wheel. So 1/2 I omega square, that is kinetic energy comes from the wheel. And you have left front wheel, left right wheel, then the forward left and forward right. So 4 wheel. And you also have a body. So body velocity, body linear velocity, and body angular velocity. Okay, that all combining together will provide you kinetic energy. So 1/2 I omega square, that is for the wheel, and 1/2 mv square, that is for a body of the robot. And by adding everything, you are able to get the total kinetic energy. And then you can have the conversion which is V equal to R omega. Okay, to convert linear velocity into angular velocity, or to map angular velocity with the linear velocity. And then subsequently you can simplify your equation in terms of any one value. So here equations are simplified in terms of mass moment of inertia and angular velocity. Okay, because when rigid body in a motion, we cannot take simply mass as a parameter. We also need mass moment of inertia as a parameter. Okay, so this equation shows the kinetic energy. Now subsequently potential energy for this kind of application is simple mgy. Okay, because your body is not going to move. Okay, move in a height direction. Suppose you are climbing on a wall, so distance from the wall is going to be remain constant. Okay, so only distance is change in height. Suppose you indicate that as a y. Okay, distance from the ground to the height. Then mgy is the only your potential energy. Okay, so you can take your kinetic energy from the previous equation, and you take this potential energy, okay, from the height which is achieved by the robot, which is y. Mg provides the weight of the robot. Okay, let me show you the equation if possible here. I will try to write in a rough manner here. So your Lagrangian equation will be something like this. So it's a partial differential equation with respect to time. Okay, with the Lagrangian equation which is denoted by L. Okay, so it is del by del T of del L Okay, del theta dot minus del L by del theta. Okay, that is equal to our force or torque value. Okay, and parameter L is called as a Lagrangian operator, which is given by difference of kinetic energy to the potential energy. Okay, so first you obtain parameter L, and then you apply this equation to know what is the force and torque value. Okay, so like this you are able to get the required dynamic equation to know the torque value. Okay, so that is what we have done here. We obtain acceleration value from this equation for left wheel as well as right wheel, and then ultimately it is given in a Newton's second law of motion, because we know that torque is equal to I into omega dot, or F is equal to ma. Okay, so that will give us the required torque value. So linear acceleration is obtained, angular acceleration is obtained, ultimately force and torques are obtained to know what is the actuator requirement here in this wall climbing robot. So this shows the concept of the wall climbing robot. We have implemented a one rotor here to create a vacuum, and a simple DC motor here to drive on the wall surface. The size and dimensions are shown here. You can easily know the concept how to implement this kind of a wall climbing robot. Of course, it's a very simple and very small kind of a robot. See, further, you need to know what kind of forces you may come across, okay, while climbing on the wall. See, this FA is a adhesion force. Okay, because see, you are selecting a centrifugal rotor to create a vacuum. So you must know what is the pressure requirement, okay, so that you are able to create the vacuum, and you are able to select the proper fan. Okay, and you know what is the rotational velocity required to create a vacuum. And for that, this adhesion force is the foremost parameter. Okay, so that is required. You also need what kind of the opposite, okay, or reaction will be obtained. So FSB is the reaction force. Further, we also need to know what is friction we have to come across. So this EF, this shows the friction force that is required. And also this FSEF is the normal reaction force, okay, based on the friction value. G is your weight of the body, which is always going downward, opposite to motion. Okay, so these are all the free body diagram or the forces shown here for this kind of a robot. Now see, always when we begin to arrive at dynamic equation, the equilibrium is the almost the first step. So it's just a balancing equation. Okay, balancing force is sigma F should be equal to 0. Okay, that is the simple meaning of equilibrium. So that's what we have done here. See, FA, as I told you, is required to know what kind of a pressure to create a vacuum, so that adhesion ensures always. So FA comes equal to the remaining other forces, okay, which is the static suction force, okay, then the friction force and normal reaction. Further, this is horizontal balance, and G is the vertical balance. Fi, sigma Fi is equal to 0. The first equation is sigma Fx equal to 0. Second equation is sigma Fi equal to 0. Okay, so this is the vertical forces that should balance the gravity. Okay, so that your robot will not fall down. Also, you need to ensure robot should not topple also. Okay, it should not rotate on the ground wall. Otherwise, it is also removed from the wall. Okay, it should not remain in contact with the wall. And for that, moment equilibrium is requirement. So sigma m should be equal to 0. Okay, so taking moment about the center point of the axle of the wheel or axle of the robot, you are able to know the sigma m equal to 0. So these three equations will help you to find out unknown value of forces. And see what we require limiting condition. So minimum adhesion force required to stick the robot on the wall at rest is this one. This we are able to obtain by solving these three equations, where V1 is the distance from the wheel and center, V2 is the distance from the tail and body center. Okay, then Kr and mu d are taken as some factor and friction. Okay, see, we keep G and Kr constant, and we can come out with some kind of a conclusion. So to minimize required necessary adhesion force, the ratio of V1 by V2 should be small as much as possible. It will cause the more driving force on the wheel tire. That is our observation here in this project. Some reduction in Hg also, the other option, reduce the distance between wall and center of gravity. Because see, as you are nearer to the wall, you can easily provide your suction. Also, but it is limited to your design. Okay. Sufficient suction reduce the support body force as much as possible. And G is the gravity force. These are the nomenclature which is used here. So these are our observation here in this equation. Dynamic analysis is also implemented here using the element principle. And see, we have taken the 4 component here in this equation, like gravity of the system, which is G, contact body sliding friction, which is this Fs, edge body sliding friction, which is this EF/EB, and inertia force, which is Ma. And from this, we are able to again derive some conclusion here. So this equation provides suction system with necessary minimum adhesion force index for designing. Okay, so ultimately we are able to know what is the force, adhesion force, and what is the requirement of the creating a suction pressure. And from this, we are able to select the proper rotor. We are able to determine RPM of the rotor, and accordingly from the torque available from the dynamic equation and the dynamic analysis, we are able to select the proper the drive motors, okay, which will take your robot, okay, either upward of the wall or downward of the wall. Okay, so these are initial mechanical analysis required before you go into the other electronics interfacing aspect. The third case here I would like to take is how to go in a bipedal motion. Okay, so again, very popular Boston Dynamics robot is shown here. But see, we are learning. Okay, so you must know the fundamental here. Okay, when you go and designing. See, if you understand the human walking, okay, while when we take our one leg, okay, in a air, other leg is on the ground. That means we are in a single support phase. Okay, one foot is in the air, other foot is on the support. So it is single support phase. Then we put our other leg on the ground. We move slightly forward, okay, before going to second leg, and in this manner we move forward, and our brain maintains stability always. Okay, so this is the normal motion. So when your both leg is on the ground and your CG slightly move forward, it is double support phase. That means your both leg on the ground. Okay, that is double support phase. So ultimately you need equation to analyze single support motion and double support motion. Okay, so that is the entire logic or entire the understanding engineering, okay, which is working behind. See, people are popularly taking inverted pendulum model or the linear pendulum model to simplify the control equation to arrive at dynamic equation. See, initially single support phase, as I told you, we one leg is on the ground, other leg is in the motion. So it is a inverted pendulum. We are only on the one leg and our entire body is moving, entire body is swinging. Okay, so it is a single support phase. Then our both leg is on the ground and then body is moving. So you are like a pendulum. Okay, simple pendulum. It is a double support phase. So this cycle repeats. Single support phase, double support phase, single support phase, double support phase, in this manner. So you can take a CG of the human, CG of the body. You have weight working downward, and you have this inertia force, okay, opposite to your motion, which is mx double dot. Mg is your support. And one popular term which we come across here in bipedal motion, which is zero moment point. Okay, so zero moment point is the point on your foot when it is on the ground, and that moment about that point should always comes to zero. Okay, all the summation of all the moments. That means these points ensure equilibrium. Okay, that is why it is called as a zero moment point. Human always have a zero moment point. Our nature has devised our motion such a way that our foot always ensures zero moment point. But you are designing the artificial motion. Okay, so you have to ensure zero moment point. Now see, again, equilibrium is the first step always. Okay, we have seen equilibrium in all the two previous cases. Here also equilibrium is implemented. Sigma m should be equal to 0. See, mx double dot inertia force, h is the height of the robot, minus your moment due to the weight mg, that should be equal to 0. That will provide you this differential equation of a motion. And we know how to solve this differential equation. See, this is the solution of differential equation, which is shown here in the third step. Of course, it's just like our normal vibration problem, and you are able to very easily get C1, C2 by providing some kind of a boundary condition. So one boundary condition is not shown here. And based on this value equation of Ax, you are able to get velocity and acceleration. So the rest of the task is very easy. Now see, coming to now, double support phase. Double support phase is a motion like a pendulum. Okay, so you also able to get this kind of a equation, same approach. Okay, you apply sigma m equal to 0, simplify equation, and you are able to get equation of a double support phase. Okay, which is now see in double support phase, both foot are on the ground. So whatever x is provided you, that is will be the 0 moment point. Okay, and suffix d indicates double support phase here. Okay, so xd is the position of cg during double support phase. Sd is the distance between cg and tip of the pendulum, and x zmpd is position of 0 moment point during double support phase. And here one constant ad is taken to govern the walking pattern. Again, solution of this differential equation is very known to us. From the mathematics, we are able to solve this. See, we have the stroke length. Okay, we know what is the step length. So S working as a step length. I can divide step length in two parts: the step length of single support phase and step length of double support phase. And summation of this SS and SD will be our total step length. Alpha is based on AD constant. Previous slide we have defined AD here, that govern your walking pattern. Okay, so that you can take as per your convenience. You just vary the value of AD and you are able to see what kind of the observation in your walking pattern, stable, not stable, that you can analyze. And from that SD can be obtained. SD is the height of the CG of the pendulum from the ground. Okay, that you are able to carry. This figure shows the simulation, okay, from the program. So all these previous equations are put in algorithm form. Value of all these parameters are decided, and then program is run. And you can see that this blue color leg is start from the back, moves on the ground, and the again come into contact with the ground. And then this red line is a single support phase, okay, until the blue leg is on above the ground in the air. And then this blue color shows the double support phase. Okay, so starting from beginning of the red to the end of double is entire complete cycle of a one step. Okay, so this total distance is S, and combination of single support phase and double support phase can be seen here. So these are the parameters taken in the simulation. Our time is taken as a 1.5. Okay, other parameters are shown here. Value of alpha, ultimately it is AD, and the different position, velocity, and acceleration graphs are shown here. And see, our equation of motion is representing harmonic motion. Okay, so that is observed here. See, your single support phase starts, harmonic motion is shown here. Then double support phase, again single support phase, so again harmonic motion is observed here. That also you can it is reflected in the velocity diagram as well as acceleration diagram. Okay, we also try to fabricate this kind of a robot, not successful, but this is the list of components shown here so that you can know what kind of other peripheral electronics device can be available. So dynamic cell motor we have tried here, the batteries, then sensor. Okay, these are all shown here. Dual shaft metal gear motor is selected here for this. 3-axis linear accelerometer motor and triple axis accelerometer motor gyro sensor is selected. Arduino Mega is utilized here. Total costing comes around 80,000 for a small robot. Okay, so you need around 1 lakh in now today's cost. This cost is something 2017 around. Okay, so that snapshot I only shown here. This is a video of the Boston Dynamics. See, you can see that very complex motion. Okay, they have implemented. But unless you understand linear inverted pendulum motion, okay, the linear pendulum motion, understanding of SSP, DSP, it is not possible to understand such a complex motion. Also, the leg design, joint design are the other aspect, okay, which we need to understand properly before going into design, which is not, of course, not a part of this discussion. Sometimes, okay, we may take that part also. So very beautiful design, okay, ultimate. See, many cleaning robots also designed by the company, particularly during this pandemic. Okay, they have come out with a very beautiful design. So this snapshot will show you the robot which is there in the medical application. They implement ultraviolet disinfection kind of a device, can completely clean by 99.9% microorganism in the hospital in a 10 minutes, and use different kind of a sensor like lidar sensor to create a map of the environment, etc. We also tried to implement in our laboratory on a small scale, of course, cleaning robot. Not many sensors are implemented here. We just try to implement the motion initially, and it is also extended to our other students right now to do it in a more sophisticated way. This kind of a 3D model initially prepared to fabricate this robot. See, many times different the way of the mechanism implemented. This robot shows the track wheel kind of a design, and also many other kind of a sensor. Like see, UV is very popular in disinfection. Hydrogen peroxide and plasma air filtration also utilized by people in some area. So hydrogen peroxide misting is very effective to full surface cover and provide room service and delivers in hotel. But some safety also we need to take care while using other kind of a disinfection measures. So quickly I will go in the understanding the equation for this kind of a track robot. A lot of mathematics I have taken, so I will not bore with many other mathematics. But see, this free body diagram I will explain to you what kind of a forces are considered here. See, we have two support on the ground. Okay, like say the wheel support here, where Fk and Nr, these are the friction force and normal reaction. Mk is the rotational moment of inertia is taken here. Then on the step, we have Fi and Ni, which is the friction force and normal reaction of other point on the step contact. G is the weight of the body. Alpha, beta, these are the all angles from the ground as well as stair. Again, see, we have to implement equilibrium. So your inertia force should be equal to some of the external forces. That is the second law of motion. You implement second law of motion and you are able to formulate your required differential equation. Okay, for the motion. This is the touching the step condition. Coming to climbing up the stair. Again, see, your forces remain same. Ni, Fi, Fk, Nr. Okay, but your angle will change. Okay, so you just implement equation in terms of angle. Now this is completely vertical condition, so friction force will not be here, only normal reaction will be taken here. And this is the leaving the ground. Okay, so now see, this wheel will not be in contact. So the friction is due to this track belt only. Okay, no ground friction or no ground normal reaction will be play a role here. Only the normal reaction will be coming from the edge of the stair, and weight of the body will remain in always. So these three equations provide you three differential equation, three motion equation, okay, for the this condition. And solving those equations, you are able to get some kind of a the condition for the track forces, the friction condition, etc. And you can easily design your system. So this is the robot which is implemented. Many kind of the helping robot are also nowadays available. So you have a wheelchair, implement a robotic arm on the wheelchair, provide a joystick or remote control in the hand of the person, and that person can easily move the robotic arm to do routine task. People also nowadays manufacturing a feeding robot. Suppose the person is suffering from the Parkinson or a stroke or not having a hand. Okay, they feel very bad when they go outside. Okay, so this kind of a robot provide a help and some kind of a empathy, emotional aspect to this kind of a people. Okay, so and see, I'm not involved in all this project, but I take a slide for you to provide you information what we can do. Okay, so this also our team try to make this kind of a robot. So initially 3D simulation. Okay, feeding robot. See, a lot of kinematics are involved here. Also, genetic algorithm is implemented to smoothen the motion of a joint. Okay, because see, here you cannot allow the food to spill off from the spoon. Okay, so to arrive at some optimum value of joint angle, genetic algorithm and many kind of other innovative technique is implemented. in solving. Human testing is being carried out here. Also, this team tried to implement image processing to calibrate distance of a person from the robot. So robot will be automatically able to find the distance of the face of the human, and accordingly the joint motion can be calibrated. This is the implementation of a image processing here. So face is detected, and then the robot will try to implement the motion. Okay, I will quickly move all these slides. Again, another kind of a version, inverted kind of a robotic manipulator. This is having a 5 degrees of freedom, and again the camera is mounted, okay, here, okay, to detect the face and calibrate the distance, position, orientation, etc. So all the 3 versions are available in the laboratory. This is a video of a commercially available kind of a robot. This kind of a robot you can operate by joystick and remote control. It's not a completely autonomous, but it is of course very simple to understand by the person and very easy to operate. Okay, people also work in a soft robotics. Again, this other people are working. Our team also working in this area, but currently I have not bring all this material because they are not successfully implemented. We are working in this area. So the Florida Atlantic University, they are working on the jellyfish. We have a MOU with FAU since long, and our students and faculty, they do exchange program very frequently. But you are able to find out what kind of a soft robotics, the material, kind of a sensors requirement, okay, the calculation of a buoyancy force, okay, the communication from the water, the preventing electronics, okay, from the water. All these are challenging tasks. IIT Indore also tried to implement with the shape memory alloy. Okay, so this is shown here, concept from the IIT Indore using shape memory alloy. This is also one of the alternative to work in this kind of a robot. Underwater robot is very popular. And as I told you, in Gujarat, Ahmedabad, we have company working in this area. So underwater robot, so they are using carbon fiber material. Thrusters are being utilized to move to provide different motion. Color camera to identify the different colors and the things under the water. Nuclear, as I told you, nuclear operations are very risky to the human life. And if you can devise robot which can go inside such area, do the communication, provide video feed, and provide some kind of a data to analyze the inspection parameters, that will always help a engineer, okay, to know the condition, okay, within such area. So this robot shown in this figure having the differential kind of a tracks, real-time CCD sensor, and other kind of a cleaning devices like sludge cleaner, filter attachments are kept here. It can be remotely controlled and perform operations. Amazon robot is very popular. They have their own cloud computing system. So warehouse application is also challenging here. May not be able to run the video, but you can go through the website and you can understand it. Robots are also being utilized in construction. Okay. See, this is the construction robot. It's a manipulator, but you can define gripper in such a way that you are able to apply in a construction. See, it is automatically taking the mortar and place the bricks in a sequence. See, again, challenge here for civil and instrumentation people is to know what kind of proportions are required, okay, to mix up the cement, sand, etc. And this can lead a completely fully autonomous kind of application. Personal mobility device, autonomous wheelchair is very popular. Okay, this also we can think. This is a very interesting topic, tomato harvesting robot. Let us see its video to understand more in detail. See, you may always have a scarcity of the labor. The time season is also varying nowadays. So always we cannot find a people to move around the farm and find a the completely ready available the fruits, vegetables, etc. See, it is only picking the red kind of a tomato. So image processing very strong here. Challenging task. You need some kind of algorithm, vision system to identify which is a grown tomato, not grown tomato, okay, etc. Also plucking mechanism, okay, so that you can pluck automatically. Storing system, so that you can store properly. See, it is very clearly visible that only red color tomato are being taken here. See, it is not currently this robot is working on the ground. Okay, so you have proper wheel system, a track system available, manipulator available. But you can think about the fruit which are at the height. Okay, where like a coconut. Okay, so people are risking their life to go the height and take the coconut. Season is very bad. Okay, sometimes. So now you think in such a way that how do you implement this kind of a mechanism for the fruits or vegetables which are at the height? See, this is a very interesting application. See, we always face the nurse and other person to if a patient is having a lift the patient from the bed. Patient is maybe in the ICU. Okay, so it is very risky for patient also. But this kind of transfer assistant robot will always helpful. See, it's very easy to take the patient from the bed and again to put on the chair. The exoskeleton is very important. It is not only for the soldier or some kind of a always in a rescue task, but suppose you have a earthquake and lot of debris, so your equipment may take a time to reach at the debris, and people may be living okay beneath the debris. So if you have an exoskeleton, okay, then people can wear very easily and they can easily remove heavy obstacle and many life can be saved in this scenario. So you also try to think in such a way that how do you design this kind of exoskeleton, okay, which is very important in the case of disaster management. This is very interesting. You might be knowing the bird. Yeah, may not be able to run this video. No problem. You go to website and you will be able to see all the details. They have also kept a little bit of technical detail of this bird for you. Okay. So with this, I will try to complete this. So thank you very much for patience listening, understanding. Okay, all the mathematics. I will invite questions from you now. You may find, yes, of course, okay, because it's not a new area. So for learning purpose, you may get library available, robot operating system, Python library. This you are able to get it very easily. And of course, the things which I show you, it is easily available in the research paper. So it is very easy for you to learn in an initial way. But you try to implement societal application, as I shown many varieties of societal application, where this kind of legged robot will be very helpful. Okay, so I will go to next question. What programming language? The question is used in program robot. So quadruped robot, we have used MATLAB programming, Simulink, combining both coding and Simulink. So initial values are obtained by coding in a MATLAB programming. Then the Simulink blocks are prepared so that this value from the workspace will be read from the Simulink block, and subsequently it is implemented in the simulation of the entire robot. See, Python is having a similar kind of a library. You can easily use Python. RO is having a very good, strong library. This is also very helpful to you. Like Gripper. Okay. See, right now we are in an initial. I think you are talking about that climbing robot. Okay. I hope it is correct. We are working on the Gripper side, but see, you need to ensure the grasping on the ladder as well as leaving the ladder. Okay, so synchronization of the gripper opening and closing is important. And also you have weight of the robot entirely depend on the gripper. Okay, suppose your one leg is in the air and the ladder, other three legs are on the ladder. So you need to ensure the design of the fingers of the gripper. Thank very much for your supplied power. Yeah. See, we are using battery right now, but simple battery may be able to provide you simple walking. When we are able to take the power, the load capacity. Okay, suppose you are designing for industry application, and your purpose is to lift a load of 50 kg or even 100 kg or more. You need a robust battery system, or you think about some kind of a device which continuously supply power to the robot. Okay, otherwise this is a major concern. Okay, to provide the power to the robot. So currently we are using DC batteries, which is commercially available right now, but we are also facing the problem of the battery drain and etc. So thanks a lot. I thankful to Info Chiefs and our management to have this opportunity and interact with you. It's a great learning session for me also. Thank you very much again. Thanks.
Thank you very much, sir. Dr. Jatin Kumar Dave, sir. A very informative and wonderful video we have seen. Now again, I would like to invite Dr. Nagendra Gajjar, sir.
Okay, almost a good afternoon to everybody. I know that I'm between you and your lunch. So I have two topic to be covered. One is the introduction to ROS, that is a robot operating system, rather not robotic operating system, but robotics consists of robot operating system. So very quickly, I'll go through why we look at operating system other than the conventional of the DOS, Windows, Linux, Ubuntu, and so on and so forth, right? So what is little extra into the operating system that we added for the purpose of robotics. So the content will be what is ROS, the advantages, what is the content or the details about the ROS consist of, the tools available with the ROS, as well as some of the exercises and references. So I won't be able to look at the exercises due to the paucity of time. So as it has been mentioned by all the other experts in the previous sessions, the robotics consists of kinematics, dynamics, planning and control, actuators, sensing and perception, actual building expertise, as well as artificial intelligence, which is the new addition into the robotics, right? So if we need to address all these aspects of the robot construction, operation, design, and implementation, then who will be helping us to integrate all this stuff? And that integration is possible with the help of a robot operating system for the purpose of management, resource planning, resource sharing, as well as including the artificial intelligence. So that's what is now, if you look at it, we cannot have that, okay, part 1 and part 2 of 5 hours, you have learned the robotics, right? So these are the individual domain that needs to be expertise or that needs to be processed for the purpose of designing robot. So what do we mean by ROS? So this has been specifically devised at the European Union. They have their kind of a Horizon 2020 as a kind of a research project consortia. So robotic research problem number one is difficult to transfer between the institutes, right? Boston Dynamic is doing something, NASA is doing something, maybe at our place ISRO is doing something, DRDO is doing something, or Japanese companies are doing some kind of a research work. Then it becomes little difficult to transfer the kind of research innovations that we have carried out. Number one. Number two problem is it is very hard to reproduce the results. So the results is to be compared, it is to be measured, it is to be standardized, then it becomes difficult at a robotics level. And the third one is the software is not maintained or outdated. So the software we need to have a kind of the version control systems, or we call it as a CVS. Now we all are little bit aware about the GitHub, which is an open source platform for maintaining our softwares, right? So if these are the problems that are existing at robotics, so they have come up with an open framework for a robotic orientation middleware geared towards reusability. So that's what is the purpose of bringing in the robot operating system. So what it consists of, normally the purpose of the operating system that it provides you a hardware abstraction, communication system, and the package management. So these are the common things if you look at any operating system, whether it is Linux or a Windows or a Apple iOS that we make use of. They provide you a platform for hardware abstraction, communication system to be carried out as interfaces, or maybe as a part of the inter-process communication. And nowadays, once again, one big issue which is coming up with the next generation hardware technology of many-core and multi-core systems, as well as a package management. How do I package my libraries and so on and so forth. So what is the robot framework is that it has a pre-installed OS is required, and right now it is a Ubuntu, which is a Linux-based platform. And then you have a collection of the different tools and the libraries. So that's what is the robot framework extra that you will be adding up your libraries on the Ubuntu platform. So if we can call it as it's a meta operating system with a middleware. So what the ROS is consist of, it is a plumbing. You have a different tools and libraries, and then you are integrating it with a Python based or a Java based or a C++ based things. And then you have a few tools. We'll be having a look at the tools, and then we'll be calling it as a capability. So capability is that what the different institutes are doing some work and adding up. And then we have, as a part of the plumbing, we have a different hardware platforms already existing. Boston Dynamics has given a platform of biped, quadruped, and kind of platforms. So that hardware platforms are existing. How can I integrate them for purpose of my design? Another integration is in terms of visualization, in terms of actuation, in terms of sensing, in terms of brain-computer interfacing, so that existing libraries and the mechanisms are available. How can I plumb it together, integrate together? And the last one is the community. So that's what we are looking at, that, okay, the people are already existing. They are doing a work on it. How do I integrate, communicate with them, and make use of their expertise? So that's what is the ROS is consisting of all four different areas to get integrated. For more details, for the curious audience, you can go to ros.org blog and ecosystem. Okay, so we have a benefits are it is open source, it's a vibrant community. It has a comprehensive library of hardware. So almost 130 robots are different type of robots. They are existing as a part of the ROS integration. And then you have a powerful ROS tools, as I mentioned. You can do the build of your software systems. You have a visualization pattern. So now Dr. Dave has mentioned about the kind of simulation that you can do and visualize your trajectory and so on and so forth. Similarly, you can do the transformation and the graph. So these are some of the tools which are already existing as a part of your Then the benefit is it has a reusable fine-grained packages, distributed system. It can support a language of C++, Python, Java, C, and so on and so forth. Maybe the Amazon robotics and the Google are also working on some of the aspects of robotics for the purpose of some of the interfaces. The open source interfaces, which also can be used, is OpenCV for image processing, Gazebo for simulation environment, and MoveIt for the path planning. So these are the kind of benefits that you achieve, that you can use the spatial libraries and the platforms for the purpose of your robot design. So what are the level of concepts in the robot operating system? You need to look at a file system, computation graph, and a community support. So if you look at it, as I mentioned, you have through the community resources, you have ROS Answers and Discourse, ROS Wiki, and ROS News as a community resource pillar. Wiki, just to give you for the time constraint, I'm just keeping this slides. Robots and research, this is also, you have a various distribution of the ROS also available, right? So you can find it out from the prompt ROS version -D. So that will tell you that what is the version distribution that you're using. You can use it on the Ubuntu 18.04 or 20.04 as the kind of platforms. Advantages I've already mentioned about it. Applications has already been discussed. More details about the applications, you can go to discourse.ros.org, but you can have agriculture, medical services, autonomous driving, factory logistics, and many more in the field. And the good part of it, this ROS can be ported on 130 different hardware robot platforms. And one of them popular from the practical and academic point of view is Turtleboard 3, which is also we have it at our Center for Robotics and Applications Automation. So as I mentioned, ROS file system level computation communication. So it has a package mechanism. So it is organized in form package. Those who are familiar with the operating system, we have a package system for the purpose of integrating everything, and then is to be deployed on the OS platform. So there you have hardware drivers, algorithms, visualization tool, and library, everything included inside. So we have one of the package as a Debian package. We have a source repositories. You can download it from the Git platform, right? So these are some of the things that you have as a part of the package. You have a source files, include files, script files, launch files, and the configure files. And then you have a workspace for specifically mentioned for the ROS, and that we call it as a Catkin workspace. So the package, what does it consist of? So this is for the installation point of view. The package, you have a CMake list, right? So these are all installation aspects. I'm just skipping it. So you have a Catkin, as I mentioned, is the workspace that you are creating for the ROS. Okay, so these are some of the steps for that. So you have a source build and development platforms and the packages that you make use of into your workspace. You have to do your environment setup file on the bash shell or a shell, right? Or you can use the Z shell. So these are some of the installation steps. For more details, definitely you can have a peer-to-peer network of the ROS processes. So you have one master node, and then you have multiple nodes that you can interact. You can do the communication, and that you call it as a publisher and subscriber. So you do the communication across your nodes that you are defining for the purpose of your operations and the controls. Then you have a graph level distribution also possible. So you have ROS executables. You can define and give the instructions for each node to be processed and communicated. Right. So these are some of the package, the functions that you use it for the purpose of programming. Right. So this is also for, yeah. I'm moving at a very fast pace. So you have ROS topic of list, echo, info, show, pub. So these are some of the graph level communication that you can do for the purpose of your degree of freedom that needs to be controlled. Okay. Okay. So you can define your network also. So you have ROS community level. So if you look at the most of the big shots, the multinationals, you have Amazon, Apex.ai, Bosch, Ubuntu, Devcom, Intel, iRobot, Microsoft, Open Robotics, Samsung, Sony, Wind River, right? So they all are part of the ROS community. You can go through the ros.org for doing all computation as well as the deployment of your things. So you have a tools such as a Qt based framework for the design of your GUI, right? So you have RQT plot, graph, bag, GUI, dashboard, and steering. So all your mechanisms, you can have it in the form of GUI. Similarly, you have a gazebo simulator, so you can create an environment in which you want to have your robot to be simulated as well as to be maneuvered. So this is an example of gazebo simulator. Then you have RVs, which is example for your visualization tool, right? So you have a robot models which can be designed. You can have a 2D, 3D cloud maps. You can have a LiDAR scan and point cloud that you want to simulate. You can and visualize it also. Other many more third-party tools are available. As we have mentioned, we have a MoveIt, we have a point cloud library, we have OpenCV as an image processing library, as well as we have a transformation TF. So these are some of the tools which can be associated with ROS. So some of the tools terminal commands are, you can have ROS core as ROS master, which you can run ROS run, which starts your ROS node. ROS launch is to start the master and node. ROS CD is you want to change your ROS directory package, as well as you want to have ROS pack as retrieving information about the available ROS pack. So these are some of the preliminary commands that you can look at once you have installed your ROS over the platform of Ubuntu. So these are the references, which is a quick reference. So mostly it is ros.org. You will get everything, but some of the things about the robots, gazebo, OpenCV, you can look it from this. So this is a very brief overview of ROS. That is Robot Operating System. Okay, I'll not take more than 5 minutes. Definitely, future of robotics is I'm projecting over you, but I say that future of robotics is you people who are going to contribute or get motivated based on this 2 days webinar series sponsored or supported by InfoChips and IESA. So the first and the foremost things about the robotics is sensors, right? So here I mentioned physical sensors, chemical, psychological. You may say psychological sensors, right? If you want to create a humanoid or you want to create any damn robot, right? It has to have a kind of a psychology also involved into the psychology of the robot as well as the psychology of the people who are using or who are going to use the robot. So it's very, very important, right? Emotional aspect. So if I want to create a robot who is going to work as a friend, he or she or the robot or a humanoid has to understand my emotions and has to act upon. So you need to create a sensor. Just imagine that how will you create a sensor which will observe the emotion of a human person. So there is one new word which has coined up. We call it as a sensor fusion. So some of the students, the professionals may be interested that how do I write an algorithm where I may be integrating 10, 15, 20 sensors and making a fusion to make a decision. Cultural aspects, the environmental aspects, the behavioral aspect, and the global scenario. So these are the kind of sensors that needs to be evolved, designed, or algorithms or fusion has to be carried out. That is the future requirement of the robotics. The other aspects of the actuators that we will be looking at is the electrical, mechanical, hydraulic, pneumatics, motion or a hybrid sensors. So there are also the actuators. What kind of actual actuators? Now, as has been mentioned by the previous experts, if I want to grasp a cup, right, a gripper has to be what kind of grippers, what kind of actuators that will be needed. So that's what is also added requirement of the future designs of the actuators. Computing, right now we say that the kind of a computing that we have shown in the previous day sessions were all single board computers with the single core computing hardware, right? But right now we talk of AI and ML. We'll be having a multi-core and many-core computing platform. So yesterday we have seen the Arduino, Raspberry Pi, but they are a kind of a single core or at least a 4-core only. But tomorrow's AI ML platforms will be requiring a NVIDIA kind of hardware where we have a many core or 2000 or 4000 cores within a single chip, which does the computation for you. So my computing has to be AI ML enabled. We'll be looking at a cloud-based system. So the Amazon Cloud or Amazon Robotics or Microsoft Robotics or Google Robotics, they will be a kind of a cloud-based systems, right? When we'll be having a swarm-based mechanism where we have 1,000 boats, right? Kilo boats are there and you need to program there, or you have say 256 drones to be communicated. Just imagine, right? Many of you, if you are from Ahmedabad, we have seen that during one of the show, there were 1,000 drones, and then they were creating a kind of an image into the air, right? On what basis do they do that? So it's a cloud-based system. We have edge computing, fog computing, IoT enabled, which is a industry 4.0 or 5.0, and the kind of a new generation interfaces, right? You people may be doing a kind of that within your computer. You have now the devices are SSD, solid state devices, right? So they have a different interface, M2 dot interfaces, right? So similarly, the new generation interfaces are also important. Now we have a Bluetooth 5.0, BLE, we have a Wi-Fi 6 and 7. So these are the new interfaces that needs to be taken care of for the purpose of computing. Standards, you name the domain and then you have a different standards to be defined, right? Right now, if we talk of the third version, which is ADAS level 5, the cars and the automotive industry has designed, but it's not deployed because standards are not properly and the laws are not properly defined. And that's what is the case. So you take any damn domain of robot application. So it's not only the engineering people, but law people also come into the picture for defining, or say medical science also will come into the picture for defining the standards for the robots. Okay, so AI and ML is going to be the next big revolution as far as the robots are concerned. So computer vision is one of the domain or area. Manipulation is also very important, that how my motor skills will be manipulated or learned. Okay, motion control and navigation. And the lastly, which is a natural language processing, how my robot learns about the natural languages that needs to be processed. So if I want to design a robot with emotions, or if I want to design the robot at a global level, so depend upon the region, it will automatically change its language, right? So these are some of the AI and ML related domain where the you can contribute for the future robot generations. So with this, I come to the end for the session. Thank you all. If any question, very quick question, maybe one or two, I'll be happy to address. Okay, so I think no further questions. Due to paucity of time, I have not covered a lot for ROS, but the links are there. Those who are interested can work on that platform. So on behalf of Nirma University Institute of Technology, I thank InfoChip and IESA for inviting us to deliver this session. First of all, let me congratulate all the participants also for their patience hearing as well as the interest in learning about the robotics, fundamentals, applications, and future. Thank you. Thank you, everybody.
Thank you very much. Thanks a lot. I'm very much thankful to Dr. Nagendra Gajjar sir, Dr. Darshita Shah, Dr. Jatin Kumar Dave, Dr. Akash Mekwan, Professor Vishal Vaidya. I'm grateful for each and every one of you. I would like to express my appreciation to everyone who worked on this event. Thank you. Thank you very much on behalf of eInfochip and Asia.